Thank you, Martin. Okay, can you hear me? It's okay?
Yes, perfect.
Okay, so well, you put me in problems talking about earthquake prediction already. There's nothing here about prediction, but
okay, this is the end of the seminar. Thank you everyone for joining, and see you next week.
But I try to show you something interesting anyway, I hope. So first, I'd like to, well, hello everyone. I hope you had nice holidays and you're ready to start a new year. First, I'd like to acknowledge my collaborators, in particular Hugo Soto, which is a PhD student finishing in Germany, now his thesis. And in this talk, I will talk about the frequency magnitude distribution of seismicity, in other words, the b-value in seismicity, for a case of an earthquake of a seismic sequence in the north of Chile. So let's see if this works. Okay, so allow me to start this talk with a somehow slightly philosophical introduction, because we are all relatively familiar with the concept of yin-yang, by which all things there are defined by their polar opposite. So we define, for example, what is bright from what is dark, what is tall from what is short, good music and bad music. And when it comes to b-value, we have believers and non-believers. So when Martin asked me whether I wanted to give the Marty Seismic seminar, I hesitated a little bit to present this topic on b-value, because I know that he's quite skeptical in relation to this kind of analysis. But then I thought that I needed to cooperate with the balance in the yin-yang of b-value. So I decided to give the talk anyway. So what is the b-value? The b-value comes from the frequency magnitude relationship defined by Gutenberg and Richter. And it's an empirical relation by which if you plot for any given region and for an enough number of earthquakes, you put the cumulative distribution of seismicity in a semi-logarithmic plot, the cumulative distribution of magnitudes of these events, you will observe that there is exponential distribution of these magnitudes, which is represented here by this straight line in this semi-logarithmic plot. So the b-value comes from the slope of the equation of this straight line. And this b-value, or the slope of this straight line, is generally close to 1 for any given region, which means that for one earthquake of magnitude 8, you will have 10 earthquakes magnitude 7, 100 earthquakes magnitude 6, and so on. So basically the b-value it's telling us the relative proportion of small earthquakes in comparison with large earthquakes. So a high b-value, a high slope, a more steep slope of the curve indicates a larger proportion of small earthquakes. And the opposite, that means the low b-values, that means a more flattened slope, indicates a larger proportion, a relative larger proportion of large earthquakes. Okay, so far so good. It looks pretty easy, but the tricky issue is that you need enough events. So to observe this kind of relationship and to obtain a good distribution of the magnitudes, you need to have enough events and a low enough magnitude of completeness, which is the minimum magnitude above which you have a complete catalog. So imagine in this case, the magnitude of completeness would be 4, and then above 4, you should have all earthquakes that occur in this area. Okay? So what are some characteristics of this frequency magnitude relationship? So it's an empirical relationship. It's based on observations. As I said before, overall it has been observed that the value in general is close to 1. but some significant variations have been measured. This relationship has been found valid in laboratory experiments from rock fracturing, as well as in field studies. There is a correlation of V-value with the tectonic stress environment. In particular, for example, in this paper, it was observed that areas with normal seismicity, normal fault seismicity, present higher values of higher V-values, and instead areas characterized by inverse faulting are related to lower, relatively lower V-values. So it comes from this and from laboratory experiments that there is an apparent inverse relationship between V-value and differential stress. Now there are many studies trying to look at the temporal variations observed in V-value, observing in seismic sequences, in particular looking at what happens, for example, before and after main shocks, or during preparatory phases for main shocks, during foreshock sequences. But there's no really a consensus of what happens with the V-value, if anything systematic happens, and then what's the meaning of that anyway. So some questions that still remain is if this correlation between this inverse relationship between V-value and differential stresses holds true. Can we use then V-value as a stress meter for the tectonic stress, for example, at the subduction interface? And if we can do that, can we use this the monitoring of V-value in real time, and what is the usability in the earthquake forecast? So let me summarize a little bit what's all about V-value with inside these three big questions: what, why, and how. So the what has relation with the observation itself, with this empirical Gutenberg-Richter exponential law, which is an observation and which describes the frequency-magnitude relationship of seismic events, of the magnitude of seismic events. As I say, the V-value is close to 1, but systematic variations do exist among different tectonic environments. The why has relation with the physical meaning, with the causes of the V-value. And we don't know what is, if there is any physical meaning behind this. As I say, it's an empirical law, but some clues come from laboratory experiments that show that the V-value is negatively correlated with differential stress. And other hypotheses include rock heterogeneity and fluid diffusion to cause variations on V-value. And the how, it's the most tricky part because it deals with the methodology to calculate the V-value. And you might think that it's quite easy, that you can just do a least square regression, for example, to fit a straight line in the distribution. But actually, it's more complicated than that, and there are many methodologies to calculate this V-value, and each one of these methodology leads to different results, some of them lacking in physical meaning. So in that sense, it's important to consider all sources of bias when you calculate the V-value, such as the magnitude of completeness, whether it is an exponential distribution or not, which seems something obvious to check, the maximum magnitude, the binning that we use when we are processing the data, and also any truncation that might exist in the higher end of the distribution. So the what, it's pretty clear. The why, we have no idea, and I think we cannot answer this question yet. And the how, it's something that we need to really be careful about it. So let's go to the case that I want to present today. This case is for an earthquake in the north of Chile, in the limit with Peru here, for a sequence of a seismic sequence in 2014, the Iquique earthquake seismic sequence. So on the 1st of April of 2014, a magnitude 8.1 tsunami-genic earthquake struck this area in northern Chile. the earthquake nucleated in an area well known as a seismic gap. There was no large earthquakes occurring in this area since 1877. And in 1877, a magnitude, approximate magnitude 8.5 earthquake occurred in this area with a rupture area of approximately 400 kilometers long. Now, the earthquake in 2014 didn't completely release all the stress accumulated in this region since 1877. In fact, it ruptured only partially a rather small area within the seismic gap. So there is still a high seismic potential remaining in the area in Northern Chile. And one particularity about this case is that there was an intense foreshock sequence before the 1st of April earthquake, which started 2 weeks before the main shock in mid-March, with an earthquake magnitude 6.7 on the 16th of March. Then on the 1st of April, we have the main shock, magnitude 8.1, and the largest aftershock of the sequence occurred 2 days after the main shock on the 3rd of April with magnitude 7.7, which is this star here. So the goal for this study is to calculate the spatio-temporal variations of bvalue and compare this distribution with the rupture area and the coupling, the seismic coupling distribution. And for that, the data set we use is 2 different earthquake catalogs. One for the interseismic period, which comprises more than 100,000 events from 2007 to March 2014. And the other catalog is for the post-seismic period, which goes from March, but actually from April 2014 to December 2014, and includes 19,000 events. Now, of course, we need to do some preprocessing of the data. We need to filter for events only above the magnitude of completeness, which we calculated to be 2.3 for both catalogs. And of course, we are using just earthquakes that are supposed to occur in the interface because we are interested in the processes occurring at the interface. So we just filter events located within 10 kilometers from the interface. And therefore, the combined catalog includes 26,000 events. So this is the frequency magnitude distribution for the interseismic catalog. Here we have the cumulative distribution indicated by these triangles here, and the straight line that fits above the magnitude of completeness, which for this case is 2.3. And the bars indicate the non-cumulative distribution of the earthquakes. And on the right side, we have the post-seismic catalog, which the magnitude of completeness in this case is around 1.7, but we wanted to be quite conservative, so we set the magnitude of completeness to 2.3 for a combined magnitude of completeness for both catalogs. And again, the triangles indicate the cumulative distribution, showing this exponential distribution, and then the non-cumulative distribution indicated by the blue bars. Okay, so this is how it looks, the cumulative distribution. But now, what's a method that we actually use for calculating p-value is not just fitting a straight line. Instead, we use the most popular method, which is the maximum likelihood method, which is a pretty simple equation. V is basically reciprocal to the difference between the average magnitude of the subset of events that we are processing minus the magnitude of completeness. Okay, so the uncertainties related to this p-value will be given by b over the square root of the number of earthquakes, the number of data points that we use for any given subset where we are calculating the p-value. So this is the most popular method to calculate p-value, and it's more robust than just doing, for example, a least square regression fitting a straight line in the cumulative distribution. So some results. This is the temporal evolution of b-value. In the upper part we have this plot A. We have the x-axis shows the time starting in 2008 and finishing at the end of 2014. The y-axis indicates the b-value, which is shown here by the blue line, right? The thick blue line. I don't know if you can notice, but there are some vertical gray lines in each data point of the blue curve, which indicates each window with its associated uncertainty. So each window here contains a fixed amount of number of events, which is in this case 2,800 events. And there is an overlap between each window of 95%, okay? And the gray vertical bar indicates the associated uncertainty. So the lower figure shows just this zoom area here in the red square, which is a zoom into the 2014 year, which is when the seismic sequence occurred, okay? And here, these red stars are showing the occurrence of the largest earthquakes during the seismic sequence, starting in mid-March with the 6.7 foreshock, the main shock here, 8.1 on the 1st of April, followed by the largest aftershock, 7.6, I think it is, 2 days after. Okay, so we see there is like the b-value during the interseismic period stays around 0.85. There is this relatively sustained increase in b-value up to mid-2011, after which the b-value is decreasing in a sustained way and very slowly decreasing, which we could interpret as stress being accumulated at the interface, until we arrive here in 2014, which we can see here in the lower panel. So in 2014, we have this b-value which kept around 0.8, but then we start the foreshock sequence, and following the first events of the foreshock sequence, we see immediately a sudden decrease of the b-value, and which increments this decrease after the main shock here, reaching very low values around 0.45. But after the main shock, we see a rapid recovery or increase of b-value back to interseismic levels, and even above the previous interseismic levels of b-value. So what are these segmented lines, horizontal segmented lines that we see here? We see in black, we see the median of the interseismic b-value, okay? Which in this case, I think is around 0.82 or something like that. Okay, this black line here. The green and the red line, segmented line, indicate plus minus 10% from the median, okay? So where does this come from? This comes from a foreshock traffic light system proposed by these authors. It's a recent paper, which proposed this three-color system as a monitoring system to differentiate basically between foreshocks and aftershocks. Now, this might sound like something kind of obvious, what is foreshock and what is aftershocks, but while this is probably a posteriori that it might seem obvious, but while the seismic sequence is occurring, is quite important, and it's not easy to, of course, we don't know whether the main shock has already passed or not. So when we are in the middle of a foreshock sequence, we don't know if we are still during foreshocks and something bigger will come, or we are already in the aftershock sequence and the largest earthquakes of the sequence has already passed or not. And of course, this is important for authorities and population to react accordingly. So these authors observed that for several sequences, and here I'm showing examples that they show for Amatrice and North Chile earthquakes, seismic sequences. They observe that during the foreshock sequence, they observe a decrease of b-value below the interseismic level, the background level, given here by the blue line, and then after the main shock, they see the recovery or the increase of the b-value. So if you have, basically, they say that while you have this decrease, and in particular when you pass this threshold, you enter in this red zone of minus 10% from the median interseismic b-value, you enter in this red zone where you need to be aware that something bigger might happen. So if you want to put some physical meaning, you might say that the stress is being accumulated, and during this foreshock sequence, and you might expect a bigger earthquake to happen. Instead, if you are in this green area, which is above plus 10% from the median interseismic b-value, you are in a kind of safe zone where you know that you are already in the aftershock sequence. So the largest earthquake has passed already. So they proposed this traffic light system to differentiate between foreshocks and foreshocks and aftershocks, and it works pretty well with our data set. So we see here that, as I say, the median for the interseismic period is around 0.82. And we see that the b-value stays within this minus 10 plus 10% of the median during the whole of the interseismic period. And when we are in when the seismic sequence starts in mid-March with this foreshock, we see the sudden decrease of b-values, and in fact we see that the b-value goes below the minus 10%, entering in this red area. And so if we were doing this in real time, you might say, okay, something bigger is coming. And in fact, on the 1st of April, the main shock occurs, after which you start to see, after 2 weeks, probably after the main shock, you start to see this recovery. And by 1.5 months after the main shock, you are back into this neutral zone, let's say, this interseismic median zone, here, where you are sure that the worst has passed already, and eventually you go even above into this green zone here. So it works pretty well for our example, but of course you need a foreshock sequence to see this. You need, if you don't have a foreshock sequence, you wouldn't know that something bigger might be coming with this main shock. Now, for the spatio-temporal variations, I have here the map in a map the spatial distribution of b-value. So this map is color coded by b-value. The blue colors indicate low b-values, and the yellowish and up to reddish colors indicate high b-value. So if we assume that low b-values indicate this negative relationship with stress, so low b-values indicate high accumulation of stress, and high b-values indicate low accumulation of stress, then we observe that this quite striking area of low b-value here, this blue area here, coincides pretty well with the eventual rupture area of the main shock. So the orange contours here are showing us the coseismic slip contours every 1 meter for the main shock, for the 1st of April main shock. And the b-value map, of course, is showing just the interseismic seismicity, not even considering the foreshock sequence here. I'm considering events just until the end of 2013, until December 2013. So before the foreshock sequence starts. So this is interseismic b-value in comparison with the coseismic rupture. And we see that the area of low b-value coincides pretty well with the eventual area of that rupture during the earthquake. Now, I'm sorry that this slide is a bit crowded, but this is just is more of the same. Each one of these windows represent a time window during the interseismic period, starting. So it's the same color scale for all of the windows, and is the b-value in the first window between 2007 and 2009. So we see that from the beginning, we are seeing all the time this area of low b-value here in the northern part. So in 2007 already, we could notice that there was, we could interpret this as the accumulation of stress in this area, okay? And this is a permanent feature during the whole of the interseismic period in each one of these windows, up to here, the window 12, which is until December 2013, so all the interseismic period, we always see the presence of this conspicuous low b-value area, and the rest of the region shows higher b-values in a quite stable way. This window here, that says window 1 to 12, is the window that I showed in the previous slide. So it's the cumulative b-value for all the previous windows from 2007 up to December 2013. And then the window 13 shows including the foreshock sequence, okay? So we see what we saw already in the temporal evolution of b-value, this remarkable decrease of b-values going to darker colors here, influenced by the foreshock sequence. Window 14 is more of the same. This window 14 finishes the day of the earthquake on the 1st of April, when the main shock occurs. And this last window here is showing the total cumulative distribution of b-value during the whole of the interseismic period. So between 2007 up to March 2014, just before the main shock. Okay. Similarly, we see here the spatio-temporal distribution of the post-seismic during the post-seismic period. So we can see here the post-seismic recovery, if you want, of b-value. We start here on the 1st of April, and of course this is a very short amount of time, in only a couple of days, because each window has a fixed amount of events. So here it's only, of course, in the aftershock period we have many events, and in only a couple of days we have enough events to produce a window. And here we see this that we're still in a time frame of low b-values, but slightly with time after the main shock we see the recovery of the area increasing the b-value. Okay. Until December 2014, and then we observe here the cumulative distribution, the spatial distribution of b-values for the post-seismic period. So we can see here basically the recovery of the b-value in the region. Now, this plot is a little bit complicated, but I'll try to explain it as well as possible. What I'm trying to show here is basically the comparison between b-value distribution, which is in this map, okay, it's just the b-values I shown before for the interseismic period, so before the foreshock sequence, okay, and the coseismic rupture. So the coseismic rupture is again shown here by these contours here, slip contours, which are every 1 meter, starting at 2 meters, I think here. The yellow star is the epicenter of the main shock. And we can see again that the area of low b-value, it coincides well with the area of coseismic slip. And what I'm showing at the right is in an histogram the same information basically. I'm showing the distribution of b-values shown by the color bars here in this area within the coseismic rupture. So basically the frequency of occurrence of b-values within this coseismic rupture. So for example, for this being between 0.45 and 0.5, b-value, we have that around 50% of the area is covered by these b-values. Okay, this is the color bars, and these box bars indicate the distribution of coseismic slip within each one of these bins of b-value. So, for example, again, for the range of 0.45 to 0.5 b-value, this circle here indicates the mean of or the median. Is it the median? The median of the coseismic slip within this range, okay, of b-value. And this is the bars indicate the quartiles of the distribution. So we can see that basically the important point here is that there is this negative correlation between coseismic slip and interseismic b-value. So we see here that as we increase in slip, in coseismic slip, we decrease in b-value. So we can associate that areas that are more stressed, therefore presenting lower b-values, are the areas that eventually will slip more during the coseismic rot. And of course, this correlation is not strikingly beautiful, but we can see something there along those lines, and it makes sense. Similarly, here I'm comparing the distribution of b-value, which is shown in the panel A, with the distribution of interseismic coupling, geodetic coupling. So this is derived from surface velocities of GPS stations. Okay, so we can see, I'm comparing these two distributions. So again, the color bars indicate the frequency distribution of b-value in the area, and the bars here, the box bars, indicate the distribution of the coupling, the geodetic coupling, within each one of these b-value ranges. So we see that there is, again, a negative correlation between interseismic coupling and interseismic b-value. As we increase the coupling here, or the other way around, as we decrease the b-value, as we go to lower values of b-value, we go increasing the tendency of coupling, which again we can explain as areas of low b-value will be indicative of areas that are accumulating more stress. So therefore present a higher degree of coupling. But of course, again, this relationship is not really beautiful. So these are the summary points of the talk. We observe the variations of b-value in space-time are interpreted in this work as variations of the stress state at the subduction interface. For this particular case, we managed to correctly differentiate between foreshocks and aftershock sequences. So there is a potential use in real time of the monitoring in b-value, and for the short-term forecasting of also of earthquakes using the monitoring of b-value. There is a special correlation between a persistent area of low interseismic b-value and the eventual rupture area, the eventual coseismic slip. There is a negative correlation between B and coseismic slip. So as we decrease b-value, we increase the coseismic slip. There is also a negative correlation between B and interseismic coupling. So as we decrease B, we increase the coupling. We are talking, of course, about interseismic B. And from this, we can propose that using b-value could be a complementary methodology, complementary to geodetic models. So in that case, we will be using b-value as an indirect stress meter to infer the accumulation of stress at the interface. This method, using it uses basically seismicity, so the calculation of b-value presents more an improved resolution offshore, particularly for subduction zones, and less assumptions and no regularization problems in comparison with geodetic methods. And the drawback is that you need a relatively dense seismic network with a good coverage. Although for this particular case, we don't have any offshore station, we only have inland stations, and it's dense, but not incredibly dense network. So it's not something it's not something extraordinary. And but the main thing is that, of course, you need enough events. So either you have an area like Northern Chile that has quite a lot of seismicity, or you need a very dense network to capture the low spectrum of seismicity. And that's it. Thank you very much.